Okay, what we're going to do now is we look at the mass spectrometer. We look at the basic workings of it, the four main parts, and we'll try a couple of example calculations from the data that the mass spectrometer provides. Right, so I've just drawn a very simplified sketch of a mass spectrometer here with the four main parts, and we'll try to label them and describe what happens at each stage. So here we are. Right, A is the electron gun. And what that does is that it takes a sample molecules and it bombards them with fast moving electron and ionizes them. So an electron will come off your sample atom or sample molecule. Right, once your sample molecules or atoms have been ionized, they're positively charged, they'll come to part B of the mass spectrometer. And part B are the negatively charged plates. Okay, and this will accelerate your ions, your positive ions, through, and they'll get propelled into the mass spectrometer here, and they'll come to this region here, part C, and part C is the electromagnet. Because the ions that you've produced, the mass spectrometer has produced, are positive, they will get deflected by the electromagnet. So their direction will change and they'll get bent around the mass spectrometer and then collected at part D. And part D is the detector. Okay. And what the detector does is that it gives an electron back to the positive ions, and that causes a current, and we get a signal in our mass spectrum. And depending on how many ions hit the detector will determine what the abundance or how much of your ions are present. Alright, so that's the basic workings of the mass spectrometer. Right, let's just come back to this. Yeah, over here. Right, here's a question. In a mass spectrometer under the same conditions, these two ions, 14N plus and 15N plus, follow different paths. State the property of these ions that causes them to follow different paths. Now remember what we said, that the ions get accelerated once they've been formed. They get accelerated by the negatively charged plates, and they come to this electromagnetic region where they get deflected. Now if it's a fairly light ion like this one here, then what will happen is those ions will go straight through and get detected by the detector, whereas slightly heavier ions like that one there will not get deflected as much because they're heavier, they have more momentum, and you'll find that they will do this. Let's try that. They will not get deflected so much and they'll just crash into the side wall here. But eventually every single ion will be collected because you can change the electromagnetic field strength. Okay, you can also change the strength of the electromagnetic plates so that they're not as accelerated as much, and that will also allow all the different ions to be collected. Right, here's another question. A gaseous sample of chromium can be analysed in a mass spectrometer. Describe briefly how positive ions are formed. And for this, you need to make sure that you write down electron gun, and you write down that it knocks out an electron. Knocks out an electron. So that's how positive ions are formed. Okay, right, next. Explain why it would be difficult to distinguish between these two ions, titanium 48 2+ and magnesium 24 1+. Now remember what I said before, that the electron gun knocks out an electron, but rarely what might happen is you might get two electrons knocked out. Okay, We'll come back to that in a minute. Right. Just drawn two examples here, look, of either an element, krypton for example, being fed into the mass spectrometer, and it'll give you the different masses of krypton that are present in a sample of krypton. You might get more, right? So a mass spectrometer will tell you how many isotopes an element has. As well as feeding in simple single elements into the mass spectrometer, you may also feed in molecules, and these molecules will also get ionized, but they will also get broken up into pieces like this, look, right, or like this. So you're going to get pieces of molecules and also charged ions, which will be detected, and it'll produce data for you. The kind of data it might produce may be a mass spectra like this, right, and or a table of data like we'll see in a question later on. So the mass spectra it produces may be something like this. On the x-axis you've always got the mass to charge ratio, and on the y-axis you've got the relative abundance or percentage abundance, one or the other. Right. What does mass to charge ratio mean? Well, simply the mass of the ion divided by its charge, m over z. Z is the charge, and z is normally +1, or rarely it could be +2 as well. Now if you look at these two ions here, mass 48 divided by the charge 2 plus, that gives you a mass to charge ratio 24, and over here mass divided by the charge is also 24 divided by the 1 this time. So if you have these two on the spectrum, their peaks would appear at the same place, so you couldn't tell them apart. Right, let's do a calculation. Here is some data that the mass spectrometer produced, and the way you would use this is simply multiply the mass to charge ratio by the percentage, like this, add the next one, 72 times 32.4, add the next one, 74 times 43.2, and divide it by all of the abundances added together, that plus that plus that. Now if it says percentage, then you just divide by 100. It's got to add up to 100. If it doesn't say percentage, just relative abundance, then you need to add up all these figures here and put it underneath there, and you'll get an answer like that. It also says in your question, you need the answer to 1 decimal place, so you must make sure you do that, otherwise you may lose a mark in the exam. Here's another question. One of the isotopes of germanium has an ion that forms a small peak in the mass spectrum, which is indistinguishable, can't tell it apart, from a peak produced by 36S+. Identify this germanium ion and explain your answer. Now, whenever you get a question like this, you know that 2+ ions must be involved. Look at this one here, the calculation. Mass over charge, 36 over 1, 36. Now, if you want to produce a value of 36 so that it's indistinguishable from this one, then the mass to charge ratio must be charge must be divided by 2, and therefore the mass has to be 72, so it gives you a value of 36. So identify this ion. Here we are, the ion is mass 72, and explain your answer, and the explanation is that the germanium 72 has a 2+ charge. Right, here's an example of a mass spectrum, a graph produced by the spectrometer. Let's use this result to calculate the average. You may want to do this and then have a look at the answer if you pause the video. Okay, and if I do the calculation now, remember it's the mass to charge ratio times the heights divided by all of the heights added together. So 2 plus 2 plus 10 plus 3. It doesn't say percentage, so it's not going to be 100. And there's the values, and you get this reading here, this calculation, the answer is 84, exactly 0.0. Notice also, as a quick little check, that the actual value that you get, in this case 84, has to be between the lowest and the highest on your spectrum or in your data. So it's got to be within the range, lowest to highest. It just so happens it's 84 here, but it could be anything, 83.3, 83.4. It could be anything, but between the lowest and the highest, right? Explain why the value you've calculated is slightly different from the relative atomic mass given on the periodic table. Now, this data came from krypton found on a meteorite, and the average came to 84. So they're asking us, why on your periodic table isn't it 84? And the reason for that is, here on Earth, the krypton samples that we have different abundances of their isotopes. Okay, so the reason why we get a different value is to do with different abundances. Here we are. This value is different to that on the periodic table because the abundances of the krypton isotopes is different from the meteorite to what you find on Earth. Okay. And the last question here. Sometimes the mass spectrum of krypton has a very small peak at 42. Explain the occurrence of this peak. And remember, what they're looking for here is for you to identify that there must be a +2 ion. Okay, and what ion would give us 42? If you divide it by 2, if you look at the results, right, it has to be the 84. So 84 divided by 2 will give you 42. Alright, so explain the occurrence of this peak. One of the ions, mass 84, had a 2+ charge. Okay, and so what we've looked at then is we've looked at the basic workings of the mass spectrometer, and we've done a couple of example calculations.